Welcome back to ECE 320A. We've been playing with Laplace transforms and inverse Laplace transforms. They have introduced this variable S. It's a complex frequency variable. What I want to try to do in this video is to try to get us a little bit better insight into what S is, or what that starts doing for us, or how to interpret this complex frequency variable S. As a reminder, we're dealing with Laplace transforms. Here's the Laplace transform definition that we've been using. It's a one-sided Laplace transform, which means that we are only concerned with functions f of t, or their value for non-negative values of time. In this particular integral, we're now weighting or comparing f of t with this expression e to the minus st. T is a real value from 0 to infinity, but now s, what is that? Well, that's a complex frequency. And what does that really do? Well, we'll show that e to the minus st can produce different kinds of waveforms, and those waveforms now are being correlated or compared with f of t. If f of t correlates well with e to the minus st, you could imagine that this integral will get very big or give you a strong result. And if f of t, the waveform, doesn't correlate very well with whatever e to the minus st is producing, then you would have a small result for those values of e to the st. Since s is now a variable, s is a complex variable, and it will be capable of assuming any value in the complex s-plane, which is this two-dimensional space. The horizontal part is the real axis, the vertical axis is the imaginary component of s. What happens now, or what does this e to the minus st look like for different values of s? We're allowing s in this Laplace transform to assume any value, and because of that, then we want to know what does e to the minus st look like at particular values to provide us some insight into this complex frequency variable s and how it's being used. But just sort of think about e to the minus st as, if s is a complex number, we'll soon see that e to the minus st corresponds to rotating phasors that might be expanding or contracting depending on what s is as a number. So what is this variable s? S is a complex frequency variable. Now try to keep in mind, as you're thinking of S, that it could be any point in this complex S-plane. It now could be any value on this particular two-dimensional plane, and in this case it might have a value of 2 plus j 2.5, if this is now j 2.5. That would be the value of s at that particular location. It would be a complex number. And keep in mind that s was actually created or invented to help us. So if you're struggling, just go back and say, well, all of this is supposed to be helping us, so how do we make this, or how do I understand this so that in fact I feel like it is helping and not making things more complicated? Let's look at another point. For example, here if we were to choose s equal to minus 2 plus j3, we would be at that particular point in the complex plane. Again, s is allowed to be any variable in the complex plane. Sometimes we want to evaluate expressions at particular locations, or we may want to say, what does this e to the st or e to the minus st doing when s assumes a particular value? Many times we will associate S or break S down into its rectangular form, or a real component and an imaginary component, and those are orthogonal, and that's what that J is. J in this expression is the square root of -1. And as you probably are aware, that square root of -1 has been introduced to help us solve all types of polynomials, not just polynomials that contain real roots. Now we can deal with a wider collection of polynomials that actually allow us to have complex or roots that have imaginary components. And the notation might be S is equal to minus sigma, that would be the real component, plus j omega. We do that because I like to a lot of times have sigma being a positive number, and most of the time we like to be evaluating expressions when S has a negative real part. That gives us the exponential decay that is associated with nice waveforms. So now let's look at what we can build once we have this complex number S. Now we're going to be putting it into an exponent that's scaled by time. So now we have this exponent e raised to a complex number S and scaled by time. So now we have e to the st, which is e to the minus, or e to the quantity minus sigma plus j omega times t. And because of what we know about exponents, we can now see that that e to the st really can be thought of as two pieces. We have, when we have a minus sigma, where sigma is positive, we have actually this decaying exponent piece, decaying exponential piece, and we have an e to the j omega t piece, which I will keep referring to as a rotating phasor, and I'll try to make that a little bit more intuitive as we move through this video. We now have e to the st as a decaying exponential and a rotating phasor. And so what you'll want to maybe be thinking about is this rotating phasor. Think of a dot in the complex S-plane. Again, this plane has a real component and an imaginary component. And for a given omega, as t counts up from 0 to infinity, this omega t gets bigger, but that now omega t means that we're spinning around, and whether or not we're decaying or expanding will influence where this point is moving as we spin around with a value of omega. If we just look at the e to the j omega t piece, forget the decay or growth factor, e to the sigma t or e to the minus sigma t. Let's forget that for now. Let's just look at what e to the j omega t looks like or is doing. We're calling it a rotating phasor, and how can we make that definition or term? If we look at the magnitude of this for any value of time t, we can now look at the magnitude using Euler. Euler allows us to rewrite this e to the jx as cosine x plus j sine x, meaning the magnitude of e to the jx, or e to the j omega t, is the same or equal to the magnitude of the real part, cosine omega t, plus j imaginary part, which is sine omega t. And we know how to calculate the magnitude of a complex number. We have the real part squared plus the imaginary part squared, or we're really now just finding the hypotenuse of a triangle that has a real part cosine omega t and an imaginary part which is orthogonal to the real part having a magnitude of sine omega t. And knowing what we know about trigonometry and trig functions, when the arguments are the same and we have cosine squared plus sine squared, that actually gives us 1. That's why we can say that this is a rotating phasor. Its magnitude is not changing if we're just concerned with the e to the j omega t piece. What's the angle? Well, the angle of e to the j omega t, again, pulling out what we know about e to the j omega t from Euler. Euler now allows us to simply write that in rectangular form. Once we have it in rectangular form, we can find the angle associated with that complex number. That's just the angle that has, or the inverse tangent of the imaginary part, which is sine omega t, over the real part, which is cosine omega t. But sine over cosine is just tangent, so now we have the inverse tangent of tangent omega t. The inverse tangent wipes themselves out, and we're just left with the argument, which is omega t. Omega has units of radians per second. T is seconds, and that makes sense. Omega t is now an angle with units of radians. And as the time evolves or grows in value, the angle is now increasing with time, and that now produces this rotating phasor. The magnitude of e to the j omega is fixed at 1, and omega tells us how fast we're spinning, and t just causes this angle to increase as a function of time. So the larger omega is, the faster that term or angle evolves, but it evolves as time marches forward from 0 to infinity. So let's look at what this expression that we can create. We can say, oh, suppose we have a function of time, v of t is equal to a magnitude, capital V sub m, e to the st. What does that tell us? Well, let's just look at some specific values or structures for s. Suppose that we wanted to look at what happens when s is equal to 0. If s is equal to 0, then we can rewrite v of t as v sub m e to the 0t, but now with an exponent of 0, e to the 0 is 1. This now gives us v of t, this time domain waveform, is no longer a function of time. This is now constant, or dc. We have a waveform now that's just constant when we had s equal to 0. Therefore, this signal that we're calling little v of t, when s was equal to 0, corresponds to a dc, or constant, signal. So if we wanted to say, oh, s equals 0, now when we hear s equals 0, you might be thinking dc, or constant. When s is equal to 0 as a complex number, that corresponds to a dc signal or a constant signal. What happens now if we look at another specific case for s? Suppose now we let s be purely imaginary and just be j omega. Then if we look at another hypothetical time domain waveform, little v of t, that's v sub m e to the st, which is j omega t, and we just talked about e to the j omega t. That's in this case, what did we have? That was just a rotating phasor. So now we have this complex spinning phasor. We now have a magnitude of v sub m, so it's a little bigger or a little less depending on what v sub m is, but it's still this phasor that's spinning around in the complex plane. And in general, it's complex because it could be anywhere in that two-dimensional space. Depending on what t is, it will then put it at a particular point in the complex plane. Let's see if we can now make a little bit more clearly understandable what's going on. We can again invoke Euler, which says that e to the jx is cosine x plus j sine of x. Therefore, if we wanted to just look, or if we want a real signal from little v of t, if we want a real signal, then we could find that v of t by just taking the real component of v sub m e to the j omega t. And what's the real component? Well, let's now expand using Euler again what v sub m e to the j omega t is. That's v sub m cosine omega t plus j v sub m sine omega t. If we take just the real part of that complex number, then little v of t becomes v sub m cosine omega t. So if we have, and this is now a sinusoidal signal with s equal to j omega, or if we now have in this complex S-plane, we said we were concerned with, or we were letting S equal j omega. Now, depending on what omega is, this might be omega 0, this might be S equal j omega 1, this might be S equal j omega 2. We're now on the imaginary axis. If S is a point on the imaginary axis, and we simply look at the real part of that complex spinning phasor, we end up with this sinusoid, in this case a cosine waveform as a function of time. So S here is dc, S here, and correspondingly S there gives rise to pure sines and cosines. Now let's step off of the complex, or step off of the imaginary axis, and look at what S looks like or leads to if S is some complex number. Let's say it's minus sigma plus j omega. Then what happens? Well, let's now look at v of t. We know it's some rotating phasor, but let's just look at the real part so that maybe we can think about this. But we now have v sub m e to the st, but now s is minus sigma plus j omega times t. This is now the real part of v sub m e to the minus sigma t. Let's distribute that t in the exponent and make the one term two exponentials that are multiplying each other together. And I hope now that you can see that we can actually factor out v sub m. Let's assume that that's a real number or a real coefficient. E to the minus sigma t is a real number. So those can be factored out of the curly bracketed term upstairs, and we now have the real part of e to the j omega t. That's now a rotating phasor with a magnitude of 1, and we now can say that, oh, now we have a v sub m e to the minus sigma t. The real part of e to the j omega t just pulls off the cosine omega t, and now v of t is this exponentially damped, there's the exponential damping, and the cosine of omega t gives us the sinusoidal part when S is equal to minus sigma plus j omega. In the time domain, then, we have some waveform that looks something like that. Here is time. Here is v of t. Our exponential damping is influenced by the e to the minus sigma piece, or part of that expression, and the oscillating piece is determined or influenced by the omega piece. So here, our time index, or our period of oscillation, is related to omega. Omega is 2 pi f, and f and t are reciprocals. So if we find the period of that oscillating waveform, we now know its frequency omega, and that omega is that omega, or the imaginary part of our complex number s. And that now says that if we are having a value of s over here in the complex s plane, now we have a real part, let's say, of minus 4, and an imaginary part of 2, so it's j2. This s is now minus 4 plus j2. We now know what the omega would be, and we know what the minus sigma is. We know the damping is e to the minus 4t, and the sinusoidal piece has a frequency of omega. All from just knowing that s is located at this point, minus 4 plus j2. Now you can hopefully see that in this Laplace transform definition, this particular part, which is now being correlated or compared with f of t, is now just a complete mix of signals, and when those signals align with f of t, we are going to get the most from capital F of s. So now this Laplace transform tells us how do we boil down what f of t is as a waveform into a frequency domain expression, or a rational expression in terms of polynomials of s. We can now say that that's going to happen as this e to the minus st correlates well or not so well with the time domain waveform f of t. And e to the minus st, what that looks like, ranges from being a DC at the origin to purely oscillatory when it's on the imaginary axis. Here's the imaginary axis. And if we're over here in the left half portion of the complex S plane, then we have a decaying, and if we're off the real line, we have a sinusoidal or an oscillating piece. If we're on the real line, we just have an exponential decay. But I hope now that you have a better feel for what e to the st looks like, all because of your understanding or insight into what s in the complex, when it's a complex frequency variable, translates into in the time domain.